Today in the workshop we're controlling servo motors with the ESP32. We'll examine several ways of connecting and using analog servo motors directly and with I2C. We'll also build a web-based interface to control a servo over Wi-Fi. We're in the right position today, so welcome to the workshop. Well, hello and welcome to the workshop, and today we are back working with servo motors again. Now, we have worked with simple analog servo motors in many of our videos, and I did a video on using servo motors with the Arduino in which I explained servo motor operation in depth. So if servos are brand new to you, you might want to check that video out first and then meet us back here. But for most of you, I think we are aware of what a servo is. It's a small DC motor that has an internal servo mechanism that measures the shaft position, and you can tell the servo motor to go to a specific angle and it'll move the shaft into that angle. Now, most servo motors do not travel a full 360 degrees. Common motors travel 180 degrees. You can also get 270 degree servo motors. There are continuous rotation servo motors, but we won't be dealing with those ones today. Now, analog servo motors are pretty easy to drive, and you can drive them with any microcontroller. We've driven them with the Arduino. You can drive them with a microcomputer, essentially anything that can make pulse width modulation. In fact, for a simple operation, you don't even need a microcontroller. You could use a couple of 555 timers to drive a servo motor and provide the PWM signal that an analog servo needs. So why would you use an ESP32? After all, it's more expensive than your average Arduino. Well, the answer would be the extra capabilities that the ESP32 has. The ESP32, of course, has a wealth of I/O ports, including some specialized ports like touch switches that you might want to use in your project. It has both analog inputs that are more sensitive than the ones on the Arduino, and it has analog outputs. But the feature of the ESP32 that I think most people are the most interested in when controlling things like servo motors are the fact that it has built-in Bluetooth and Wi-Fi capabilities, so we can remote control our servo motors as well, and we will be doing that a little later on in this video. But first of all, we're going to start off with a brief recap of servo motors and how they relate to the ESP32. The ESP32 is actually a good match for a servo motor. Servo motors require pulse width modulation control signals, and the ESP32 has multiple PWM outputs. The position of a servo motor shaft is controlled by the pulse width, and the ESP32 has several precision timers allowing very precise control over pulse width. Small low-cost servos are very suitable for battery-powered designs. The ESP32 is also suitable for battery-powered designs, having several low power and standby modes. There are many practical applications for servo motors, ranging from robotics to toys. With a wide variety of I/O ports, sensors, and communications options, the ESP32 is also suitable for many different applications. One typical use of servo motors is in radio-controlled hobby projects. With integrated Wi-Fi and Bluetooth, the ESP32 is ideal for creating remote control projects. A typical analog servo motor has a 3-wire connection. The first connection is the control input, where the pulse width modulation signal is sent to control the servo. On most servo motors, this is an orange wire. Next, the power wire. Typically, most servos use 5 to 6 volts DC, but you should check your servo motor specifications to be certain of this. And finally, the ground wire, which on most servo motors is brown. The color coding, however, is not standard. Many servo motors use a black wire for the ground wire, and many servos use a white wire for the control input. Most hobby servo motors use 5 to 6 volts DC for powering. making them ideal for battery-powered applications. Most of these servo motors will work properly with 3.3 volt logic, but again you should check the specifications of your servo to be certain. It is a good idea to power your servo motors independently from the ESP32. It's not a very good plan to share the power line between any motor and a microcontroller. Many of the ESP32 pins have multiple functions, so make certain when you're picking a port to use for pulse width modulation that that port isn't used for another function. So now let's start working with servo motors and the ESP32. And so here's an example of some servo motors that you could use in these experiments. Now this one over here is the most common type of servo you're going to find for hobbyists. It's called an SG90, and it's available just about everywhere on eBay, on Amazon, and probably your local electronics store as well. Now there also is an MG90, which is functionally identical but uses metal gears instead of the plastic ones used on the SG90. So if you have something that is going to have a risk of having some load applied against it, you're probably better off using the MG90. Now this one looks a lot like an SG90, but actually this isn't an SG90. It's a modified one, and these are commonly available, and they're called continuous rotation servo motors. These are not the type of servos we're going to be using today. A continuous rotation one can continually go in 360 degrees, and the pulse width modulation signal determines the speed, not the position on these motors. So because they look alike and because they have the same connectors, be aware that these motors, which are marked as continuous servos, are not the same as these servos which only travel from 0 to 180 degrees. Another very common servo motor here is the Hi-Tech HS422, and this, as you can see, is a larger servo motor with more torque than the SG90, but it is driven the same way and can use the same control signals. Now over here I've got a little device that I picked up. I think this was literally about $2 or $3. They're very inexpensive and they're called servo testers. Again, Amazon and eBay are great places for them, and they allow you to test out servo motors. You apply power on this side, connect your servo on that side, and you can use this knob to determine the position. It's also got a couple of other tests you can do, like homing the servo, etc. And these are very popular with radio controlled hobbyists who use boats or aircraft that have a lot of servo motors. They carry one of these with them just to make certain their servo motors are okay. And finally, this package of goodies over here is a package of things called horns and arms for servos. Let's just rip the plastic over here to get this off. And as you can see, it's got all sorts of attachments for the servo motor, and these of course allow you to attach devices to your servo, and you're going to end up with a whole bunch of extras. Never throw these out because you will eventually find a use for them. And so there you go, a few examples of servo motors that we can use in our ESP32 experiments. So now let's begin using the ESP32 to drive our servo motors, and as you'll see, coding for it is very similar to the way it would work with an Arduino, but there is one caveat. The servo library that comes with the Arduino IDE is incompatible with the ESP32, so that gives you a couple of choices as to how to work with servos. You can work with them manually because all you're doing is creating a pulse width modulation signal, and you can certainly do that in code, but that can get a little bit messy. So you're better off using a library in most cases. Now, there is an LED library that comes with the ESP32, and many people have used that to drive servo motors because that library drives LED with pulse width modulation signals, and that's pretty similar to the type of a signal that we need for our servo. So by adjusting a few parameters like the PWM frequency, you can use the LED libraries to drive servo motors. But there are also replacement servo motor libraries that replace the IDE Servo Library, and that's the route that I'm going. There are a couple of really popular ones, and the one that I've chosen is called ESP32Servo. And this library I like because it is updated frequently. In fact, as of this recording period, it was updated merely 2 months ago, and some of these other libraries haven't been updated for a few years. So this means to me that this is an active product that is going to be continually looked for bugs and things like that. And you can install this library from your Arduino IDE. So let's go and take a look at the ESP32Servo library, and we'll run a couple of the examples just to see how we drive servos with the ESP32. For our first experiment, you're going to need an ESP32 module based upon the ESP-WR00M32 chip. Now, you do not have to use the identical module that I am doing, but please note that the pinouts will be different on your module if this is the case, and go by the I/O connection numbers that I'm using, not the actual pins on my module when you're hooking yours up. You'll also, of course, need a servo motor. I'm using a small SG90 servo, but really any servo motor will suffice. You'll need a power supply for this servo. Most servo motors work well on 5 to 6 volts DC, so you could even use battery power if you wished. Finally, we're going to need a potentiometer. I used a 10K linear taper pot. We'll begin by connecting the ground connection on the servo to the negative or ground connection on the power supply. Note that on many servo motors this is a brown wire and not a black wire. We'll connect the servo's power wire, which is generally a red wire, to the positive connection on the power supply. The servo's control wire, which is generally orange but can also be white, will be connected to the IO18 pin on the ESP32 module. We're also going to tie the ground from the ESP32 to the negative or ground side of the power supply. This is a critical connection, so don't forget it. We will also ground one side of the potentiometer. The other side of the potentiometer will be connected to the 3.3 volt pin on the ESP32. Now you can power the ESP32 with this 3.3 volt pin, but if you are powering it with 5 volts or using your computer's USB port to power it, this will become a 3.3 volt output. Finally, the wiper of the potentiometer is connected to the IO34 pin on the ESP32. And so now that we've hooked everything up, let's go and take a look at some code we'll use to drive our servo motor. In order to work with servo motors on the ESP32 using the Arduino IDE, we're going to have to make a couple of modifications to our IDE. Now, first of all, you want to make certain that you're using a relatively recent version of the Arduino IDE. I'm currently using version 1.8.13, which as of this filming point, July 2020, is the most current version for Linux, so make certain you've got a current release of the IDE. Next, you're going to need to modify the IDE in order to accept all the ESP32 boards, and I've covered that in my previous video on the ESP32. You can also check out the article accompanying this video on the DroneBotWorkshop.com website, and that will tell you how you can modify your IDE and its board manager. Once you've done that, we are going to need to install the library for the servos on the ESP32. But before we do that, I want to show you something. I'm going to go down into File over here and go into Examples and go down to the very bottom, and you'll notice I've got a section called Incompatible. Now, these are incompatible examples with the board that I've currently selected, which is an ESP32 board. And you'll notice I've got 4 of them. I know they're kind of tiny and near the bottom of the screen, but if you can see, the third one on that list is the Servo Library. This is the Arduino Servo Library, which is incompatible with the ESP32. So when you're using the ESP32 board manager, this library and a number of other ones that I have are not available to you. So we will need to install a library for the ESP32. So what we're going to do is go under Sketch and go into Include Library and go into our library manager by clicking Manage Libraries. Once your library manager is open, go to the top and type in ESP32Servo. The library that comes up is the ESP32Servo Library by Kevin Harrington and John K. Bennett. Now, I've already installed mine, but if you haven't, you'll have an install button over here, and you can click it to install the library. Once you've done that, we can take a look at one of the examples that comes with the library. So we'll go to File, we'll go to Examples, and we'll go to Examples and Customs Libraries, and we have ESP32Servo here. And as you can see, there's a number of examples, including, strangely enough, a couple of ones that don't have to do with servo motors. We're going to concentrate on the ones that do, and the first one we're going to use is the sweep example. Now, the sweep example is a clone of the Arduino sweep example, and all it does is it takes the servo and rotates it from 0 to 180 degrees and then returns it to the other end and goes back and forth, back and forth. And you've probably used this with the Arduino in a servo if you've worked with servos before. Now, we'll go over the code for this example. It's very simple, really. First, we include our library, so we start by including the ESP32Servo Library. Then we create an object called myServo, and that represents our servo motor. We can represent, as it says here, up to 16 servo motor objects using this. Now, then we give it an integer that we're going to use to represent the position in degrees. And so we're going to start off at 0 degrees. And then we have something called servo pin, an integer that represents the GPIO pin that we are using. And as we're using GPIO 18, we're using that. But as it says over here, you can include a number of other different GPIOs that are PWM compatible. Now, in the setup, we need to allocate all of the timers. You will need to do this every time that you're using this library, and so we do that over here. And we can also set the period that we are using for this servo, and we've set it to 50 Hertz, which gives us period pulse widths of 20 milliseconds, and that's exactly what we want. Now, after that, we do a myServo attach, and this again is very similar to the original servo library. We pass it the servo pin, and we also pass it two different parameters, and I'm going to explain those parameters in detail in a few moments, so we will be coming back to that. Then we go into the loop, and the loop is very simple. We just do two for loops, essentially. The first one counts from 0 to 180 in increments of 1, and it writes that position out to the servo. So it's going to step up in increments of 1 from 0 to 180. There's a 15 millisecond delay that's applied after that, and then it goes back through the for loop until it's up to the 180 degree point. And then after that, it goes through another for loop, which is exactly backwards. It goes from 180 to the position of 0, and it decrements by 1 and does exactly the same thing. So this will cause the servo motor to sweep back and forth. So let's load that up to our ESP32. And remember, in a lot of ESP32 modules, there's a button you're going to have to press in order to make the upload work. I'm going to load that, and we'll take a look at how it works. Now, here's my ESP32 module on a solderless breadboard. You can see the servo motor over here, and the potentiometer that we're going to be using in our next experiment is also connected. Now, I've also connected one of these breadboard power supply units up to the breadboard, and this is a very convenient way of powering the servo motor and eventually the ESP32 itself. Now, the ESP32 right now is being powered by the USB connector from my computer, so I've disconnected the 3.3 volt line from the 3.3 volt rail. These rails are set to 3.3 and these are set to 5 volts. The 5 volt line here is being used exclusively to power my servo motor. And so it also has a power switch on it, and the code is already running, so all I need to do is hit this power switch, and we should see our servo motor go through the sweep function. And it is indeed going back and forth. However, if you're observant, you will notice that we seem to have a little problem over here. The sweep was supposed to sweep at a full 180 degrees, and I think you can see from that this is clearly not going a full 180 degrees. In fact, it's probably going not a lot more than 90 degrees. So there's a bit of a problem, but there is a way to fix that. So let's go back to the code, and I'll show you what we need to do in order to get the full 180 degree sweep from our servo motor. So let's take a look at the code and see what we can do to resolve the issue of the servo motor not going a full 180 degrees during the sweep. The answer to the problem is right down here on this line, and it's where you do the attach. Now, when you attach the pin that the servo motor is going to be connected to, the GPIO pin. There are also two other parameters that you're probably not that familiar with because they aren't used in the Arduino implementation of the Servo library. These parameters determine the pulse width for the minimum and maximum position of the servo. So in this case, 1000 microseconds is the width of the pulse sent down the control line in order to bring the servo to the 0 position, and 2000 microseconds is the pulse width that is sent down the line in order to put the servo at the 180 degree position. And it's pretty linear, so you can infer from this that 1500 microseconds should put the servo in the 90 degree position, etc., etc. Now these values can be altered for different servo motors, and that's the key. The first one, as I said, represents the 0 position, so instead of 1000, I'm going to reduce that to 500. And instead of 2000, I'm going to bump that up a bit to 2400. And now we're going to upload this to the ESP32, run our sweep example again, and see what effect it has had on the movement of the servo motor. So let's try the sweep again, this time with our adjusted parameters in the code. I'll start this. And as you can see, this is much better. I think it is going now a full 180 degrees. And of course, you can fine-tune those parameters for your servo motor to get an exact 180 degree turn over here. And every servo motor will be a little different. Even two servo motors of the same model number can require slight adjustments. And by being able to do this, you can actually get some very accurate positioning using this code. So now that we've seen this, let's go and move on to another code example. Now the next example sketch from the ESP32 Servo Library that we're going to look at is the knob example. And the knob example just emulates the knob sketch that comes as an example with the Arduino Servo Library. And it's a very simple sketch. It takes the value from the potentiometer and in turn relates that to the position of the servo motor shaft. So as you move the pot, the servo motor shaft will move accordingly. Now we start off again by including our library, the ESP32 Servo Library, and creating an object to represent the servo motor and defining the pin that we have it connected to, GPIO pin number 18. We also define another integer called pot pin, and that represents the pin that we are connecting the analog input in. We're going to use analog input GPIO pin 34. The next parameter, ADC max, is the maximum value that we can get from the analog to digital converter. Now, the analog to digital converter in the ESP32 is a 12-bit converter, as opposed to the 10-bit one that you would be used to in an Arduino. And so with a 12-bit converter, we have 4,096 possible values, as opposed to 1,024 that we would with a 10-bit. However, on the ESP32, by using low-level code, you can reduce that to as little as 9 bits. And so if you do, you would need to change this number. But by default, it's set to 12 bits, and you would leave it at 4096. We also have another integer called val, and that's just simply the value that we are reading off the potentiometer. Now, we have the setup over here that starts off exactly the same way that we did in our last sketch. We allocate all of our timers, we set the period to 50 Hertz, and then we do an attach. And if you notice this, I haven't changed this. They've actually set this up for an SG90, and they use the same values I did of 500 and 2400 for the minimum and maximum position of the servo motor. Then we go into the loop, and the loop is extraordinarily simple. We do an analog read of the value on the pot pin and assign that to the val variable. And then we map that in order to change its value from 0 to the ADC max, which in our case is 4096, to 0 to 180. So a very simple use of the map command. We write that value to the servo, and then we add a 200 millisecond delay. And we have to add a longer delay because we need to account for the fact that if we move the pot very fast, the servo probably has a bit of time it's going to take take to get to that position. So a very simple sketch. We'll upload it to the ESP32 and we'll look at it in action. So here I am about ready to demonstrate the knob sketch, and again the same breadboard setup. Now one thing to note is that I currently am powering the ESP32 from the connection to my computer from the USB cable, so I have its 3.3 volts disconnected from the power supply rail. These are at 3.3 volts. However, that is what I'm using for the potentiometer because we want it to go from 0 to 3.3 and not 0 to 5 volts. 5 volts is still powering the servo, of course, and if I were to disconnect this cable from the computer, I would need to connect the power, that's this red line, to the 3.3 volt rail. So having said that, let's go and see if this works, and it does. As I'm moving the pot, I can put the servo into different positions. A very simple sketch, and it just emulates the original Arduino knob sketch, but it'll give you a good idea of how to work with servo motors with the ESP32. So now that we've seen that, let's move on to the next step. Now sometimes we have a need to drive quite a few servo motors, and the ESP32 can drive a good number of servos through its I/O pins, but occasionally you'll need to drive even more than the ESP32 or any other microcontroller can handle, and for this a good component to use is the PCA9685 module. Now we have used these modules before with the Arduino. It's an I2C module that has 16 PWM outputs and can drive 16 servo motors. It is also used for LEDs to drive 16 LED strips, and so it's very, very versatile. But if 16 isn't enough, you can cascade these modules because you can select the I2C address. In fact, in theory, you can have up to 62 of these modules, and as each of them can support 16 servos, that will give you 992 servo motors, which should be enough for pretty well any project. But remember, this is an I2C device, and the ESP32 has more than one I2C bus, so if you really need more than 992, there's an option for that as well. By the way, if you do have a project that needs more than 992 servo motors, please post a picture of it up on the DroneBot Workshop forum, and perhaps a picture of that 200 ampere power supply that you're using to drive all your servo motors. Now, I don't have anywhere near that number of servo motors to drive. In fact, I'm going to limit my demonstration to just 2 servo motors, but the principle I'm using can be used for any number of servo motors with the PCA9685. So let's go and take a look at this module and see how we can use it with the ESP32. Now here are a couple of PCA9685 modules. I've got one here that is completely assembled and one that comes unassembled, so to speak, because all of the headers and the terminal for the power are not connected to it. You'll also see there's a large capacitor over here that isn't on this board. This board can actually have some advantages. If you want to mount this, for example, onto a printed circuit board, you could take the edge connectors, and these edge connectors are actually duplicated on both sides, so you can daisy chain these modules, and you could put the pins underneath the board if you wanted to, like that, if you wanted to solder it down onto, let's say, a printed circuit board. The capacitor is used sort of as a current sink for the motors, and it's a good idea to have that in. If your motors are chattering, this can sometimes fix the problem, although that's not the only reason servo motors will chatter. It also is good if you have a sudden need for a lot of torque. This can hold a lot of energy, and this has a 1000 microfarad capacitor already installed in it, and there's room for it on this board as well. But the main connections, as I said, are repeated on both sides, and so the I2C and the power connections, etc. And this terminal over here is where you would attach the power for your servo motors. So you're going to want to use a power supply that has enough capability to power all of your motors. And here, of course, is where you attach the servos. Now, this board can also be used for purposes other than servo motors. It's quite common to use this with LEDs as well and use PWM to drive them. So you can attach LEDs or LED strips onto this as well. So a very versatile and useful board. Let's go and see how we use it with the ESP32. For this experiment, once again, we'll require an ESP32 module, and we'll be using a PCA9685 16-channel PWM controller. We're also going to need a couple of servo motors. I'm just using 2 servo motors, but the PCA9685 can support up to 16 of them. We'll need a power supply for those servo motors. Again, you could use battery powers for a supply that is generally 5 to 6 volts DC. You're going to need a couple of pull-up resistors as well for the I2C lines. These should be approximately 2.4K as we are using 3.3 volt I2C. We'll begin by connecting the I021 pin on the ESP32 to the SDA connection on the PCA9685 module. I/O pin 22 will be connected to the SCL line on the PCA9685. We'll connect the 3.3 volt connection on the ESP32 to the VCC connection on the module. Make sure not to use the V+ connection, as that's just another connection to the servo power supply. We will connect the ground from the ESP32 to the ground connection on the module. Next, we'll connect both of our pull-up resistors from the 3.3 volt line to the SDA and SCL lines respectively. Now we can connect the power supply up to the power connector on the PCA9685 module. And finally, we can attach our servo motors to the module. I'm showing my motors in position 0 and 12, but that's just because it was easier to illustrate here. And you can actually use any of the connections that you want to and just account for them in code. So now let's take a look at the code we can use to run our servo motors with the ESP32 and the PCA9685. Now, to work with the PCA9685, you're going to need to install one additional library. This is the Adafruit PWM Servo Driver Library, and you can get this library through your library manager and install it in the identical fashion that we did earlier with the Servo Library for the ESP32. Now, this is the same PWM Servo Driver Library that is used with the Arduino, so if you've already used this device with the Arduino, you'll already have this library in your Arduino IDE. So our sketch starts off by including the wire library, which of course is the library that allows communications on I2C. The PWM Servo Library is installed next, and it's dependent upon that wire library for its communications. Then we are going to create an object to represent our PCA9685 module, and you can create as many of these objects as you wish in order to represent different modules. The modules just need to have a different I2C address. So I'm calling mine PCA9685, and I'm using this address, hexadecimal 40, which is the default I2C address of these modules if you don't use any of those jumpers to change it. Now, we're going to define a couple of constants over here, and these constants determine the number of ticks we are going to use. Now, what's a tick, you might ask? Well, what happens with the PCA9685 is first you set it to a frequency, and the frequency determines what the pulse width is going to be. And then if you want to determine how much of the pulse is high and how much of the pulse is low, the pulse is divided up into 496 sections, and they are each called a tick, and you can tell it when you want to start going high, at what point. So you can say, I want to start going high, let's say at tick number 100, and I want to come back low at tick number 1000. It'll produce a small pulse. And so we need to define the minimum and maximum values that we are going to be using in ticks, and this will determine the pulse width. Now, this is identical to what we were doing earlier with the servo library to define the minimum and maximum pulse width so that we knew whether the servo was at the 0 point and the 180 point. Now, you're going to need to experiment with these values over here. These are the values that I'm currently using for my servo motor, but every servo is going to be a bit different, and I don't even know if these are necessarily perfect, but you can start off with these values. Then we're going to define a constant that just represents each of the servo motors. Now remember, you can have up to 16 of these on the PCA9685. I've attached mine to connection number 0 and to connection number 12. So I've done SER0 is connected to 0, SER1 is connected to 12. Of course, you can change this around and add or subtract as many of them as you wish. We'll also need a variable to hold the speed for each of those motors, and I'm calling mine PWM0 and PWM1. Now in the setup, it's pretty simple. We set up our serial monitor. We're just going to use that to monitor the actual angle that we're driving our servo to. We're going to print onto the serial monitor. We're going to initialize the PCA9685, and then we are going to set its frequency. Now this is important because it can determine a pulse width frequency of a great range, and we're going to set ours to 50 Hertz. And 50 Hertz is pretty well average for a servo motor, but again, you can experiment with this if you're finding you're getting chatter or noise in your motors. Now in the loop, I have to confess, I got a bit lazy. I should have actually written a function because I'm basically doing the same thing here 4 times over. And what I've done actually is I've just blatantly stolen the code from the sweep sketch that we looked at earlier. And if you recall, the sweep sketch took the servo from 0 to 180, and then it took the servo from 180 to 0, and it kept repeating itself. I'm doing that, except I have 4 sections now because I have 2 servo motors. So this is a pretty simple way, and again, not necessarily the best coding, but it gets the job done. So I'm starting off by going from 0 to 180, and I'm using a map command to determine the PWM value from those servo min and servo max that I had before. Now this is the key to working with the PCA9685 over here. I've got my PCA9685 object, and I'm using the set PWM method, and this is the way that you actually address one of the servos. So I'm addressing servo 0, which happens to be on connection number 0, and then this is the start point and the end point of the number of ticks you are using. So we always start at the 0 point, and then the end point will be this PWM value, and that will determine the width of the pulse that we are sending. Then we're going to also print that pulse width out to the position out to the serial monitor, and we'll add a little delay to allow the motor to actually move into position. Then we go to motor 1 and do it in the opposite direction, go back to motor 0, move it the other way, and motor 1 the other way, and just repeat it. And so it's a relatively simple sketch. Let's go and take a look at it in action now. And so here's our PCA9685 set up with the ESP32. As you notice, I've got it onto a breadboard. Because it had a right angle connector, I just mounted it directly to the breadboard. It's being powered from the 3.3 volts on the ESP32. The ESP32 itself is being powered by the computer. Back over here, I've just got 4 AA batteries, which is a really good way of powering servo motors, and those are connected to the power terminal on the PCA9685. And as you can see, my servo motors are indeed going back and forth. And if you look at my serial monitor, you will also see that you can see the position of the motors being displayed on the serial monitor, the position in degrees. And so it does seem to work. Now we're just controlling 2 motors over here, but this device is capable of controlling 16, and because you can cascade them, you can control basically as many servo motors as you want with these modules and just an I2C connection. So another great way of controlling servos with the ESP32. Now, as I mentioned at the beginning of the video, one of the main reasons someone would elect to use an ESP32 over an Arduino for controlling a servo is the built-in Wi-Fi and Bluetooth capabilities, and this would allow us to remote control our servo, and we're going to do exactly that over a web page. Now, in order to get the code for this, what I did is I visited probably the most popular, if not the best resource for ESP32 on the internet, and that is the Random Nerd Tutorials website. It's run by a couple, Rui and Sarah Santos, out in Portugal, and they have excellent information about the ESP32 and, for that matter, the ESP8266. And so I'd highly advise that you check out their website and their YouTube channel for some great information about the ESP32. Now, I've taken some code that Rui has written, I've changed it a bit because I'm using a different library, and I styled my interface a little bit differently, but otherwise it's basically the same code. So let's go and take a look at what we need to do to control a servo motor over the ESP32 with a web-based interface. For our remote-controlled servo experiment, we can use the identical hookup we used in our initial tests. As the potentiometer isn't actually required in this experiment, you can remove it if you wish. Now let's take a look at the code we'll use to remotely control our servo motor through the ESP32. So here's our remote Wi-Fi control sketch, and I'll go over it bit by bit just to show you how this actually works. It's a good example of how to do any type of web server control with the ESP32 actually. We start off by including the Wi-Fi library. This is the built-in library, of course, to attach to the Wi-Fi, and it comes with the ESP32, so there's nothing to install there. And we've already installed our ESP32Servo Library, which we call over here as well. Again, we create an object for this servo called myServo, and we set up a constant for the GPIO pin that we're using for this servo, and in our case we're using pin 18. Then you'll need to add your network credentials over here, your SSID and the password for your network. We're going to start off a web server on port number 80, that's standard HTTP. We'll need a variable to store the HTTP request header information, and we'll also need variables to get the get values. Now the get values are the values that are going to be returned via AJAX to our web server. So when someone moves the slider on the web page, it's going to change a value, and we're going to store them into these variables. We're also going to use the current time and previous time using the millis function, and the millis function tells you the amount of time that has elapsed in milliseconds since the device has been started. And this is a way, by taking the current and previous time, that we can measure time delays without having to use a delay function. And there are a lot of problems with using delay, so this is actually a much better way of doing time delays, etc. Now, in the setup, we'll go once again and allocate the timers for our servo motors, and we'll set the frequency to it as well to 50 Hertz as we did before. And again, we'll attach to the servo. Now, I've used the values that I came up with for my SG90 servo motor, and you can change these for the minimum and maximum travel of your servo if necessary. We're also going to start the serial monitor, and we'll connect the Wi-Fi, and we'll get the SSID and password sent to the Wi-Fi over here, and print our local IP address onto the serial monitor. And this is very important, of course, because we're going to need to know on our web client where it is we have to look for our web server. So we're going to open the serial monitor at the beginning of this and get the IP address that's been assigned to us. Now we're going to go in the loop, and in the loop basically we do two things. We build a web page and we listen for incoming GET requests from the client. And so that's basically what our loop is doing over here. I'm not going to go through it step by step because there's a bit to it, but basically if you're looking for the web page itself, it starts to build over here, and we use a client print ln of course being with a carriage return, to print out the actual HTML that's going to be our web page. And so you can see over here, this is actually the web page. I've got it divided into the headers, the HTML headers, the CSS, etc. And I've got the page displayed a little bit easier to read on the article that accompanies this video in standard HTML. So if you want to go through and change some of the colors or change the way the controls work, etc., etc., you can take a look at that, and then you can edit it over here because it's a little hard to read the actual HTML over here. There's also JavaScript at the end here as well, and then we end the page. Now we look for get data. If there's data in the header, this is what we want. This means somebody has moved the control and has sent us back some data. So we're going to get that data. We're going to combine these two bits together and get something we call the value string, and that's the string of the position we want to put the motor in there. And then we're going to write that to the servo. Now we have to use a toInt to convert that to an integer because it is not coming in as an integer, it's coming in as a string. And then we can go and print it to the serial monitor just to see what the value actually is. And that's an important troubleshooting technique. If you can't get the motor to move, you can take a look at your serial monitor and see if you're getting a value back over here. And then after that, we break out of the HTTP and end everything and stop the client. We'll print client disconnected, and we'll go and do it over again and wait for a client to connect again. So this is basically how you build a web server with an ESP32, and in our case, how you get instructions back that we can pass on to control the servo motor. So now let's go and take a look at it in action. Alright, well I have everything hooked up on the breadboard. It's essentially the same arrangement I had in the initial experiments. I've removed the potentiometer and I'm using the 5 volt from the breadboard power supply to power the servo motor. The ESP32 is being powered by the connection to the computer via the USB. And I've just reset my ESP32, and if you look up on the screen where we see our serial monitor, you'll see the Wi-Fi is connected and I have an address over here, 192.168.1.121, and I can copy that address and go over to a web browser and I can paste that address into here. And we have our servo control screen over here. And so this is the web page that's being generated by the ESP32. And if I move this, as you can see, my servo motor is moving. Now if we go back over to the serial monitor, what we can see is we keep seeing client disconnected after every page, but notice these value numbers, the 180 up over here, the 80 over here, the 33 over here. Let's go back onto our web page and you can see 33 is where we are here. So if I move this again, I get to 99. I'll go back to my serial monitor and there's my value of 99. So we're passing values back to the web server and these values are being used to move the servo motor. So this is a very simple yet effective way of controlling a servo over a web server using an ESP32. Alright, well that about wraps up everything for today. I hope that you enjoyed our look at using servo motors with the ESP32, and given that you could use the Wi-Fi and Bluetooth as a remote, I'm sure it's opened your eyes to a number of different project possibilities. Now if you want some more information about the stuff that we covered today, or if perhaps you'd like to get the code samples that I used, you'll find all of that on the article that accompanies this video on the DronebotWorkshop.com website, and there's a link below the video to that article. There's also a link below the video to the DroneBot Workshop forums, which is a great place to talk with like-minded individuals about all sorts of electronic projects, be they ESP32, Arduino, Raspberry Pi, or anything to do with this wonderful world of DIY electronics. So I'd be thrilled if you would join the forum and join in on the conversation. Also, speaking of a conversation, I do send out a newsletter, and there's a link to that below. It's not a sales letter or anything, just a way of keeping in touch with you and letting you know what is going on here in the workshop. And if you have not subscribed to the YouTube channel, please do so. I would be very appreciative if you would do that. Just click on the subscribe button below the video or on the robot in the corner of the video, and after you do, also click on that bell notification so that you'll be notified every time that I make a new video. So until we meet the next time, please take care of yourselves, please stay safe, and we will see you again very soon here in the DroneBot Workshop. Goodbye for now.